stuff. And now let me present Dr. Marta Berholts. She's a researcher based in Estonia. Her research is focused on fundamental studies of the interaction of atoms, molecules, and clusters with X-rays and ultraviolet radiation. She is interested in clarifying the working mechanisms of radiosensitizers used in cancer therapy and understanding the radiation damage in DNA and other biomolecules. Dr. Berholts got her PhD in materials and science from Tartu and Turku universities in 2018. After that, she spent 2 years as a postdoctoral researcher at Uppsala University in Sweden, where she worked in a laser laboratory on a time-resolved experiment that resulted in the development of new method to accurately measure short intervals of time using so-called quantum watch. And this talk is about this quantum watch. Please, Dr. Berholts, the stage is yours.
Thank you so much. Thank you for a very nice introduction. Thank you to the organizers for inviting me. I'm super happy, and thank you for giving me the earliest slot today to present my talk, because now we can smoothly proceed from our alarm clocks to quantum watches. And you know, they say that if your talk is more than 15 minutes, then you have to give an outline, you have to explain people what you're going to talk about. And this is a very simple outline, because we're going to talk about quantum watches. And the introduction, I will tell you how this quantum watch is different from the rest clocks. And in the experiment, I will show you how we did it. And spoiler alert, we're going to talk about Rydberg atoms, lasers, some exciting stuff. And then I will sneak in a couple of equations that we use to describe the experimental observations. And then we compare the theory with the experiment to see how it overlaps or not. And in the end, there will be a short summary where we will discuss where can we use this quantum watch, and where it will be beneficial to use it. Okay, so I worked on this project during my postdoctoral studies in Uppsala University in Sweden, and this project was funded by Estonian Research Council and was called Photo-Induced Effects in Atomic and Molecular Systems. But I usually call this project my COVID project, because the time when I come to Sweden, there is a COVID-19 outbreak happening. Like after 1 month that I'm there, the COVID outbreak. Super fun. So some findings are now published in the paper in the Journal of Physical Review Research. The title is Quantum Watch and its Intrinsic Proof of Accuracy. You can see here this colorful circle with the number 237. It tells you how much attention in the media the paper got, and it was extremely popular. So this number tells you how many times the paper was mentioned by Twitter, Facebook, blogs, news outlets, and so on. So you can imagine that I was super popular for about 1 week. Everybody wanted to have an interview with me. And the journalists from New Scientist, they interviewed me and also other colleagues who were participating in the research. And then they wrote an article about our work. So Quantum Watch is a completely new way of measuring time, it was called. And they even called our watch as super accurate quantum stopwatch on the cover. So for me, as a scientist who is not used to any kind of attention, that was really exciting. And after that, there was an avalanche of different articles coming from different places from the internet, and of course I was collecting all of them. And they had some catchy titles like "Scientists invent quantum watch, a mind-bending new way to measure time," or "Scientists devised quantum watch that measures time in a fundamentally different way." And you see, this were English articles. Then I was also browsing some articles that were appearing in foreign languages. And it's interesting because they all had some kind of picture of a clock or a watch, how it's supposed to look. But in reality, I know how it looks. And it's huge. You cannot wear it on your wrist. So the quantum watch is like a big one-room apartment, okay? So this we clarified. Okay, now let me explain you in simple terms the concept of the quantum watch. And if we think about the other traditional clocks, how they work, then they usually have some starting point, so time zero. And then what they do, they measure some very precise period of times, and then we see how much time has passed. But for the quantum watch, you don't have to use a counter. Just imagine that, yeah, there is time zero, but you don't have to know where it is because you have a time fingerprint. So in some way, you're able to create a time fingerprint that shows you exactly how much time has passed. And, the easiest analogy, how to think about it, is to think about tape measure. So tape measure measures distance. So for the distance, we have this kind of method, because when you measure the distance with a really long tape measure, like 50,000 meters or so, you measure the distance, you see the number on the tape measure, and you don't have to think that where it started, because you know where the tape measure started, 15,000 meters back somewhere. So it's the same thing with the quantum watch. We have our time. So before it was not possible to measure time in such a way, but now with the quantum watch we are able to do that. We don't care about the time zero. We receive time fingerprint. Okay, now let's talk more in details how it is done. And here you can see quantum watch recipe. And the first step is very easy. We have to take an atom. So we took helium. Helium is very simple atom. It has a nucleus and 2 electrons that are orbiting that nucleus. Then the second step is a little bit more complicated. So what we have to do, we have to create a wave packet composed of coherent superposition of multiple Reedberg states. So for non-experts, maybe a lot of unfamiliar words, but in simple terms, what we have to do, we have to put an electron from that helium atom into a higher energy state by, for example, giving it some photon or some XUV laser pulse, so that we could bring that electron to a higher energy level. And the key thing here is that we have to create a superposition of states. And the electron could be in multiple states at the same time, so in multiple energy levels. And it was explained before using Schrödinger cat, right? Because the cat could be both dead and alive in a box with a poison. And you never know what state the cat is until you open the box. So this is something like that when we put an electron into superposition of different levels. We don't know exactly which level electron occupies. Okay, next we have to monitor the superposition state somehow, and the easiest way to do it is to send in a second laser pulse. And in that way, when we have 2 lasers, this method is called pump probe photoelectron spectroscopy. So we have 2 lasers. One excites the system by bringing the electron to higher energy state, and the other pulse comes with some delay in time and checks what is going on with the system. And what it does, the second pulse ionizes the electron. So electron is getting away from the atom and is being detected. So this is what we did, actually, during my postdoc project. We did this kind of palm probe experiment, and it resulted in quantum watch. Okay, now let's talk why Reedberg states are so useful for the quantum watch application. So as we already know, Rydberg states are highly excited states with energies that follow Rydberg formula. It's here. So they are states that are converging at the ionization threshold of the atom. So you could see on this diagram that the electrons are in the ground states, which means they are very close to the nucleus. But when they are excited, they are moving further away from the nucleus. And they are occupying this Reedberg states, which have really nice scaling properties. And the scaling properties of the Rydberg atoms, they highly dependent on the primary quantum number n. So basically the n shows you how far away the electron is from the nucleus. So it could be 2, 3, 5, and so on, up to infinity. Because here at the ionization threshold, there are so many levels that we could say that there are infinite amount of levels. And you could see that the properties are changing. For example, binding energy and energy level spacing are decreasing with n. You could see on the diagram the energy spacing is really decreasing. The orbital radius, polarizability, and radiative lifetime, on the other hand, are increasing. The higher is the Rydberg state. So these Rydberg atoms are very useful to study fundamental laws of physics, and they are used in quantum technology. Okay, so now let's do a thought experiment. We send in a first laser pulse. We excite an electron from the ground state to the level 13p, and we are using very narrow band laser excitation. So we are making sure that we are exciting only one level, not superposition. And then we send in a second photon, and after that we measure that electron that got emitted, and we measure it in time, and this is what we see. We see that there is a continuous signal. At every time there is an electron emitted. Okay, and we see that continuous signal for as long as the lifetime of this 13p level allows us, and the lifetime is about 130 nanosecond. And the higher the energy state of the Rydberg atom, the higher is the lifetime as well. So it changes, it grows. But so you know that, like here I show the time in femtoseconds, and femtoseconds is extremely small duration of time. If you compare it for a second, so that means that a femtosecond is to a second, as a second is to 32 million years. So for us people, we cannot imagine that small amount of time. For us, a blink of an eye is a very short period of time, but blink of an eye is like 3 milliseconds. It's actually quite long. So the femtosecond is just a small fraction of it. Okay, so this is one example when...
Sorry, may I interrupt with a question?
Yes, maybe?
You said the electron is emitted, but you also said you only take single atom, is that right?
Yes.
So you have at most 2 electrons to play with, so don't you run out? Like, how can you...
No, we all have constant supply of atoms. So there is one atom, but we still can follow the evolution of this created signal over time. But we have a constant supply of atoms. There's one atom after the other. Okay, so now next example, when we have multiple Rydberg state excitation. And in that case, we use a broader laser which could create a superposition of two levels, so level 13 and 14p, for example. And you see there is some difference between the levels, delta E, and so we have a laser that is broader than that difference. In that case, we could create this coherent superposition of states. And then when we send in the second pulse, what is happening, because electron is also a wave, so it has all the wave properties, and waves, light can interfere. And what we will see in this measured signal, we would see so-called quantum bits. So we will see that at certain times there are a lot of electrons, then there is no electrons, then there is again a lot of electrons. And this quantum bits, they would have a certain period that will depend on the separation of the energy level. So this is fascinating. But this is only for the two levels. But in the quantum watch, what we did, we actually excited all of the levels up to this continuum with a really broad band energy pulse. And the question is, what will happen when we do that? In our research, we were trying to understand it, to do the experiment, to see how it will look. And here you could see the distribution of the probabilities, like, where electron could be in which level. So from 10, it starts growing, and then it maximizes at around 20, and then it decays up to 50. So they have different probabilities, and we can send in the second pulse and check where the electron now exactly. Okay, so now let's follow some simple examples first before we go into crazy stuff. And so here are two electrons and they interfere. So we will see this kind of picture when we have excitation of level 13 and 14. So the energy difference between these two levels is just 11 milli-electron volts. And so we have this period. And on the bottom, you see the same result as it is here, but it is integrated along the kinetic energy of the electrons. So we don't care actually about the kinetic energy. What we are caring about is the total amount of the electrons, right? So in certain cases we have a lot of electrons and then no. So this bottom figure shows us that. But if we excite higher energy levels, then we will see that the difference between the levels is becoming smaller and the period is larger. So the interference picture that we see over time is changing. Okay, now let's go to 3 levels. So 3 levels are superimposed and the interference picture becomes a bit more complicated. So we have some long features and short features. But if you look at this 2D image, then you could see that it is still quite periodic in time. Okay, then we excite simultaneously 4 levels, and again, the picture becomes even more complicated. So the conclusion that we can make from here is that the number of Reedberg states in the wave packet, so in the superposition, will define the complexity of its time dependence. And the more levels there are in the superposition, the more complex will be the interference pattern that we observe on the detector. Okay, so now let's see how we were able to achieve these conditions. And the experiment was done in HELIOS laboratory, and HELIOS is high energy laser induced overtone source located in Uppsala, Sweden. So I spent my corona time there in the lab mostly, and what we had a commercial laser, the titanium sapphire laser, that was producing pulses of 800 nanometers or 1.55 eV. They were very short pulses, just 45 femtoseconds. And the laser output was split into 2 different branches. So we had a pump line and we had a probe line. So the pump line, so 80% of the laser output was used to create higher energy radiation. And higher energy radiation was created here in this small gas chamber. And then the other 20% of the laser intensity was used as a probe line. So the second pulse, infrared pulse, to ionize electrons. And there was a delay stage. And we were able to move this delay stage, which contains 2 mirrors. And by moving the delay stage, we were able to delay when the second pulse comes. So we were able to write the time delay by physically moving the delay stage by short amount of times of micrometers. And then these 2 pulses, they eventually met in the main chamber. They met there, and here you could see me and my colleague Shushmita actually aligning the probe line. And this is this electron spectrometer that we were using, and we were looking now inside the main chamber. And inside the main chamber, we had this gas cell. It's a cylindrical gas cell with some openings for the laser beams to come in and out, and also for electrons to exit and be detected by the detector. So this is how quantum watch looks like. And you see that there is a constant supply of helium through this gas cell. So the helium is always there. And so in the end, what we were able to achieve these properties for the pulses. For the first XUV pulse, we were able to achieve central energy of 24.6 eV, which is exactly at the ionization threshold of helium atom. This is exactly what we want. And quite broad bandwidth, 0.1 eV. For the second pulse, the central energy was 1.55. It was enough to ionize the electron from the excited state. The bandwidth was a bit smaller. So this is what we got. Now time has come to see what kind of interference pattern we were able to observe when we did that experiment. When we put into the superposition lots of levels starting from 10 to infinity. And this what we saw in the experiment. This kind of picture. And I remember that we were super excited to see it because we knew that we will see quantum bits, but we didn't know how they would look like because at that point we didn't have theory yet. And then, we were measuring this experiment and every time step took 1 minute and we were like following it because finally everything works and we were sitting and saying, oh, one oscillation comes, the second comes, they are all different and they have such intricate structure. So here in this experiment you see that we measured for 7 picoseconds this experiment. And we were super excited to see that this pattern is so intricate and complicated. But then we started thinking, how can we describe it with the theory? And we did a simulation. And simulation actually was able to capture all the properties of the experiments, almost. It looked the same. And so we were super happy about it, of course. And since, we had to call this interference pattern somehow. So we decided to come up with a name, and the name was CUPS. And there were 2 reasons why we called it CUPS, because who doesn't like CUPS? And the second reason is that it stands for quasi-unique bit signatures, meaning that the signatures are unique for each time. So they are kind of time fingerprints of our quantum watch. So now, as I promised, I will show some equations, because I know that for some people it's really important to see the equation, because if they don't see the equation, they don't understand anything. And here is the equation of this initial state, the superposition of the electrons. And the cat is always there because it means the superposition. We have this wave packet, the superposition of electron states. And in this wave packet, there are lots of levels. They have their own energy, their own phase, and their own amplitude. So each level has different characteristics that we could capture with the theory. But then, so this was the first equation. And the second equation was to describe the time-dependent photoelectron emission amplitude for a specific photoelectron that is leaving the system. And we used this equation. So basically, we took a certain photoelectron kinetic energy and calculated all the possible paths for the pump and probe to get to that energy. And then sum the amplitudes together to receive the output signal that you just saw, this interesting, intricate signal. So now let's compare it with the theory, because what we did next, we actually measured for a longer time. So now you could see this measurement of these quasi-unique signatures for 81 picosecond. That was a long measurement. It was more than 2 days that we had to measure it. And then we started applying theory on top of that, the theory that I just showed to you. And what we did, we used some different equations to calculate the energies of these Reedberg states. And in the first equation, we didn't use any quantum defect, so we calculated it as it is for hydrogen, where there is one electron. And then with the other theory, we actually introduced the quantum defect, because helium has 2 electrons, there is electron correlation, and we have to account for it. And you see that in the first 5 picosecond evolution, the both theories actually are doing pretty well, but the discrepancies starting to appear at higher delays. And here you could see that the theory without quantum defect actually starts failing. So it does not capture some of the big peaks of the experiment anymore. While the theory with quantum defect, as it should be, is very good. It captures the experiment almost perfectly. And this is really fascinating, because when I was matching both of them, the experiment and the theory, I found that there was a delay, like a shift of about 90 femtoseconds between the two. And this is interesting because we could assume that the theoretical time, so the theory is right, so theory shows the correct time, because there is such a great quantitative agreement with the experiment, which means that whatever we saw in the shift, this is misalignment of the delay stage. So the delay stage that we use to control the second pulse. What this experiment showed us that actually our experiment was flawed, so when we compared it to the theory. So we were losing about 1 femtosecond per picosecond using the delay stage. But the quantum watch showed us the correct time. So we were able to assign for it. And this is extremely interesting, because if we look at all of the energies that we used and focus on this level 12 energy, then the difference between the energy levels is really small. It's 0.2 milli-electron volts. But, you know, one matches theory and the other does not. So these are extremely small differences, and we can capture that by the theory. So we know the math really well, and the math predicts what we see. And of course, since this is a quantum watch, and since we saw this very rich oscillation pattern, we were thinking, like, what can we do with that? How can it be useful? And then we thought that, yeah, I mean, I actually was, you know, sitting one day and trying to understand, like, how to promote the paper, what to do, how to bring it to the next level. And then I was looking when I can see where the period starts over again, and then we see the same pattern again, and I was not able to find it. And then we decided to test. Maybe, you know, the signatures are really unique to each time. And what we did in that test, we took from this really long experiment, 80 picosecond experiment, we took 24 slices, different slices in different locations. And I remember exactly well why 24, because my computer that I was using had 12 cores. So simultaneously I was able to calculate only 12 points. And 12 points seemed like not enough, so we increased the amount of points by 2. And so my computer was struggling to find the overlaps between the theory and the experiment. Like, I think for 12 hours it took to run every slice. But what we did, and what you can see now, that we took these slices, we varied the size of the slice. So we varied it from 0.7 picosecond to 3 picosecond. And then we compared it to a simulated, much longer, 10 nanosecond long spectrum. So we compared, like, so we were looking for this slice on the 10 nanosecond time scale. That's why it took so long, you know, to find. And then what we found out that if you take a slice that is longer than 1.7 picosecond, then the correct time is found in 100% of cases. And then, of course, if you reduce the slice, then it becomes worse, and then it does not find the correct time all the time. So this was a nice result, and this kind of convinced us and the referees of the papers that this quantum watch is actually providing a time fingerprint. And I know that I have about 10 minutes left, but this is already the last slide, so we will conclude now. And here you could see these two pictures that we were talking about today. So the first one is very boring, periodic harmonic oscillation pattern. You cannot get time fingerprint from that. With here, like, you have to calculate from zero, like you have to calculate each of this tick quantum bit. But in this picture, we are having superposition of 40 levels. Can you imagine? Like, electron is in 40 states simultaneously, and this produces this extremely interesting interference pattern that is able to provide a time fingerprint. So very suitable for the quantum watch materials. So it provides time fingerprint, like, you know, each person is individual, have their own fingerprints, and the quantum watch for each time provides its own pattern that is specific only for that time. And we could understand that. And the main requirements for that quantum watch, that it should consist from a large amount of Reedberg states, and the Reedberg states, of course, they should be long-lived. That means that we could use this quantum watch over a broader time scale. And Rydberg states, they could live to about microseconds. So in principle, we could use that watch on the scale of microseconds. And what are the advantages then? Like, if you don't have to measure time zero, how it could be useful? So, as I showed you, it turned out that the timekeeping is artifact-free. So when we compare it to the theory, we can see that these quantum bits calculated, simulated quantum bits are actually more accurate than the delay stage. So this kind of quantum watch could be as a calibration tool in any pump probe experiment to show the real time and do not rely, you know, on a delay stage that you cannot control the exact time. And the second aspect that is very beneficial is that, of course, the quantum watch provides a timestamp, so you don't have to find time zero. And it could be very important for certain pump probe experiments, because it's not always trivial to find time zero, and then people want to study properties of their quantum systems on this short time scale, but they don't know exactly in which time it is happening. So in order to be accurate in time, in order to know the time, you don't always have to know the time zero. And that's a very big bonus, and it's quite unique property of that quantum watch. And of course, I did not do all of it alone, so I had a team. And here you could see their pictures. I'm super grateful to Robert, who is a HELIOS lab engineer. So he was helping me a lot with all the problems that I had in the lab. Like I wanted to shift the laser energy to lower because we couldn't reach this higher Reedberg States. And then he was helping me with that. And then there was also Shushmita and Hampus, who were postdocs, also like me, during the time of this experiment. They were also helping in the lab a lot. And then Ronny Knut is very important person for this work because he did a lot of theory for that. And together we did a lot of pair programming to actually test the quantum watch. And Johan was my supervisor, so this is the person who helped me actually, who invited me to go to Sweden and to work in his lab. So I'm also very grateful to him. Okay, with that I will wrap up my talk, and aitäh tähelepanu eest, which from Estonian means thank you for your attention.
Thank you for your interesting talk. What again was the time resolution, so the smallest amount of time you can measure with this method, and have you played with other atoms or highly ionized ions and stuff like this?
Yeah, that's actually a very interesting question because yes, you know, Rydberg atoms, they could be formed from any atoms and even molecules and ions. So in principle, you could, like this quantum watch could serve a different pump probe experiment depending on what kind of photon energies one wants to use. And of course you could use other atoms because, you know, when this electron is excited to a very high energy state, it feels like it's a hydrogen. Like it feels like I'm a hydrogen, I'm so far away from the nucleus. This property is translatable to all of the other systems. And for the ions, for example, we also were thinking how we could accommodate the quantum watch to different experiments by, for example, if somebody doesn't have the XUV pump that has as high energy as we had. So in that case, they could use some other gases like neon or xenon, some inert gases. But of course, they would have to calculate the quantum defect for these specific atoms for the quantum watch to work. But it is possible, and for the ions, if you're using ions, then you could increase the XUV pump that you're using, the first pulse. So yeah, we were thinking about it, and it's possible, but we did not test it, because I only had 2 years, and now actually the lab is transforming. So they are buying a new laser, and now they are, you know, doing all of this stuff to accommodate a new laser and build the lab again so that they could run 2 lasers at the same time. And maybe later we could test it.
Thanks for the talk. At the end you said that one advantage is that you don't have to find time zero in pump probe experiments. Could you explain a little more about that point?
Why is it so advantageous? Or
I just have no idea about pump probe experiments.
Okay.
Maybe I think
so
that's the
time
point.
zero in a pump probe experiment means that we have 2 pulses, right? And time zero is when the 2 pulses, when there is no delay between the 2 pulses, they are simultaneously in the interaction region. So that means that it's time zero. And then we delay the second pulse with the delay stage, and then the pulse is arriving later. And then this is the way how we could, you know, follow the time evolution of our system. I know that in some experiments, like when people are studying some magnetic properties of the samples, it's not that easy to find this time zero. Because in gas experiments, it's easy, you have a sideband, like this very intense signal when the pulses are overlapping. But with magnetic materials, you could have some effect, but you are not sure exactly where the time zero is. And it's impossible to calculate it otherwise. And that's why the quantum watch now has this opportunity to help researchers to find their time zero and to be more specific about the timings, what are happening in their experiments with their materials.
Yes. So first of all, thanks a lot for the very, very nice talk. It was very, very interesting. I have actually two questions. So that example that you showed with the two interacting states, did you really measure that, or was it more?
This I did simulate.
Oh, okay.
For these specific states,
yeah.
I used the proper energies, I simulated those. But these simple wave packets with just two states, they are already studied too well. People know about it. And that's why it's not interesting anymore, you know.
Okay. And I guess it would be probably hard to have just the right bandwidth to excite just those two states and adjust the energy correctly. Yeah. And the other thing is, how did you describe the electron-electron interaction in the helium atom? Like with what theory exactly?
So actually this theory was already developed, and we actually just took the equations from one paper written by Drake, we used Reed's expansion formula to calculate the quantum defects for each level. It's just like that, yes.
All right, thanks.
Hey, so also thank you for your interesting talk, and I'm curious about if you know or can imagine some application areas for this in the future outside of research, or maybe that it comes from research, but...
Well, outside of research is maybe a little bit hard to imagine right now, but I'm not saying that it won't be possible. It's just that maybe we don't know how to think about it yet. But now what I see that specifically for pump probe experiments, the quantum watch could be a really nice calibration tool and really precise. So I think I forgot to answer one of your question, and you asked that what is the accuracy, or what can we measure? So we can measure up to 8 femtosecond accuracy. 8 femtosecond is really, really small amount. So the quantum watch is extremely accurate in this time scale that it can be used. And this provides, this unique opportunity for keeping time more accurately, more precisely, and describing, therefore, the fundamental things that scientists are observing in their experiments with more precision.
Thank you.
Hi, thanks also from me. So I'm wondering about an application inside research. So do I understand correctly that in your experiment you have the pumping and the probing in the same place? Is that correct?
Yes.
Yes.
So they are overlapped in time and in space.
Yeah. Is it practically feasible to pump and probe in different places? So I'm wondering whether this could be used for time-of-flight experiments, where I say I have my helium atom at x at time 0, which I can determine by where my pumping happens, and then check somewhere else whether I can probe the electron there, and from the signature then determine how long it took to get there. Is something like this possible?
I don't think it's possible. For the pump probe effect to be really seen, the pulses have to be overlapped in time and space. If they are not overlapped, then you're not you're losing correlation between your processes. You can pump something and then you probe something else, so you lose that information. So that's why they have to be overlapped at all times, and then you follow, the evolution of your system. If they are not overlapped, you won't see any pump probe effect, unfortunately.
Okay, thanks.
Yeah, thanks a lot. Somewhat of a technical question. I was wondering, in spectroscopical applications I'm familiar with, one usually has to deal with Doppler broadening of the transitions due to the thermal motion of the atoms. Is that not an issue here?
That do you mean that there is some kind of motion and
yeah, like the atom is moving slightly towards the laser, slightly away from it, and thus these different frequencies.
Yeah. Because we also we had a gas flowing through the gas cell, right? It was constantly moving and flowing, but maybe there are some effects, but they are very minor, at least on the time delays that we have studied here. I don't know about, because there could be some dispersion also happening with the wave packet, but we have not the chance to measure for the, this longer time delay. So I cannot answer that, but in principle it could influence the outcome. But even if it influences the outcome, it could be accounted for in the theory. So we could, take these effects and simulate, like put them into the simulation, and then still, get this accurate CUPS time that we could.
Okay, thank you.
Maybe one more question regarding this Doppler effect. I mean, you integrated over the energies, no? You did not do an energy, resolved measurement. You just measured the time delays. So the Doppler effect would just shift.
But we actually also measured energies, right? If you remember these colorful pictures, because on the y-axis there was an energy, so electrokinetic energy. So we measured the energies, and the time.
But then you had the integrated spectra, like the red line that you showed, so that was energy independent. So I think the Doppler effect should be ruled out then, no? I guess. Okay.
No,
I'm not sure either.
No.
Now, a complete layman's question, but on the diagram you showed of the experimental setup, I was kind of missing the second laser, right? You had the EUV laser on that diagram, and then the delay stage, which creates the delay between the pumping and the probing, right? But shouldn't the probing be done by the NIR laser? How does that work?
So we have one laser, and we split whatever the laser output is into two branches, using beam splitters, and in that way, so your question is completely right. Like I would also be asking that if I wouldn't work there. But we have this 1.55 EV laser that we used for the infrared laser with the delay stage. But the other 80% of the laser are coming into high harmonic generation cell, and so the magic is happening there. That from this 1.55 EV, we are producing the harmonics, and we are able to produce higher energy with this high harmonic generation process. And this is what we do in that cell, but it's all happening using one laser.
Okay, thank you.
Yeah.
Okay, then maybe one question from me. So your watch is already taking a room and requires quantum measurements. How can you use it in other experiments to measure actually time? Because how can you avoid the interference between the actual experiment and your watch?
Yeah, that's a bit difficult, right? But in principle, you could make a supply of helium to your interaction region, right? You could do that. It's possible. Of course, it would require some engineering, how you exactly construct the gas cell to put helium in and then place it in the proper position for your experiment. But this is already for other scientists to think about.
All right, anyone else? Okay, great. Then thank you very much for the great lecture, and thank you for the attention.